Dr. Manuel Borca, who for almost 20 years has been the lead scientist for African swine fever and classical swine fever at Plum Island Animal Disease Center. And prior to his current position, he was part of the original African swine fever program at Plum Island in the early to mid-90s. His research has focused on identification of determinants of virulence, pathogenesis, and vaccine development for both African swine fever and classical swine fever viruses. Manuel will now give his seminar on an update on live attenuated vaccines. I think you're muted, Manuel.
Now you can hear me?
Yep, now I can hear you.
Okay, sorry. If there is anything that everybody that working in vaccine development in African swine fever agree is that animals that are inoculated with live attenuated strain of viruses are protected against the challenge, at least with the homologous isolate. The point here is how we produce those live attenuated vaccines. And let me just, for the purpose of classifying, let me present three different ways to produce this virus. One is by just using field isolate that has low virulence. Second is by attenuating the virus by culture passages. So the virus, when they get adapted to the virus, pass it to the culture, lose the virulence. And the third method is by genetically engineer viruses that by deleting specific genes, they became attenuated. I'm going to go through all these three classifications, and I will give some examples, and I give some also some examples of the advantage and disadvantage of each of them. Let's start with the low virulent field isolate. This having several examples of people working with this. I just pick one. It's a paper from Mibus and Ardiri from Plum Island back in 1980. And this person, what they did is they used Brazilians and Dominican Republic isolate that were not completely virulent, and they inoculate animals. And what happened is that the surviving animals, they were challenged with highly virulent virus from the same region, and they get protected. They even went a little bit further, and they used Lipon-16 as a kind of heterologous challenge, and still they got some degree of protection. So, and studies like that have been for a while, and actually from this experiment, there were 2 or 3 different viruses that were all natural isolate that start being used as a model to study the production of protections and the mechanisms of induction of immunity in African swine fever. And some of these viruses, I will talk a little bit of some of them, are like the isolate or T88-3. I think this isolate was isolated from soft ticks in Portugal. This is a non-absorbing virus. And interesting, this virus produces a strong protection when it's used to immunize animals, and the animals are challenged with an homologous virus that is called ORT88.1. And the problem with this virus is that, like in many others that are natural isolates, that they still have some residual virulence. And there have been work done, and I will refer one from the group of Linda Dixon, where they tried to get rid of this residual virulence by deleting specific genes that have been previously described as involved in the virulence. And I'm talking specifically in the case of this paper of 2 genes that were removed, that were what have been demonstrated before that attenuate Spanish isolate. I'm talking about the removal of NL and UK genes. But what Linda did is that she produced a virus that is called Delta DP2. And what happened is that this virus is still, after the deletion of these genes, still present a residual virulence. And also, and the worst scenario was, and that is happening, that is very frequent, and it happened to us in Plum Island also, once that the genes were deleted, they not only didn't show elimination of the residual virulence, but also there were a clear decrease in the ability of the T88 virus to induce protection. So genetic manipulation, even in those natural isolate attenuated isolates had to be a little bit careful. Another example of these low virulent isolates are the NHP68, that is also a non-absorbing virus isolate in Portugal. And that interesting, half of the animals that were inoculated with this virus present some kind of chronic form of disease. And the surviving pigs, or the pigs that were not heavily affected, actually were very, very well protected with the challenge with an homologous isolate, the Lisbon 60. And because that, as in the case of the ORT-ADA, this model also became a very good system to study immunity and mechanisms of protections against the disease. As I said, the virus also has a strong level of residual virulence, and in a paper from the laboratory of Yolanda Rovisha, they tried the same thing that they tried Linda with the ORT-ADA, that is, get rid of that level of residual virulence. And what she did actually, and the group, is to delete 4 different genes that were previously shown to be involved in viral-host interaction and in the immunomodulation of the host. And unfortunately, what they see is that in all the cases, they still see presence of residual virulence in several of the pigs that were inoculated, either with the wild-type virus, with the parental virus, or with the recombinant virus. An interesting issue is that all of them, in this case, they were protected when they were challenged with Lisbon 60. And an interesting result in this paper was that animals that were inoculated with the parental virus, the NHP68 attenuated, and they were challenged with Lisbon 60. Interesting, when they were challenged with Armenia of 07, that is a derivative of the Georgia virus, they were also protected. So that was an interesting presence of cross protection that I thought that was interesting to point it out. Now, again, the problem with this virus, as the other one, was the residual virulence that cannot be easily solved, a problem that cannot be easily solved. The last virus that I'm going to give as an example is also a natural isolate, also non-absorbing. That is a virus that have been isolated and worked by the group of Dr. Jose Manuel Sanchez Vizcaíno in Madrid. And this is basically a virus that was isolated in Latvia from a wild boar. And what this group show is that oral vaccination with this virus protects over 90% of the wild boars that were challenged with the virulent Armenia 07. And this results, the authors proposed that this could be a vaccine that can be used in wild boar. But there is also a paper that has been published by the same group where they inoculate this virus to domestic pigs. And what happened is that both animals in some way develop residual virulence, develop same signs of disease that were a mild disease, but they were disease. And also when they put 4 animals in contact with these 2 directly inoculated animals, half of them, 2, also developed sign of the disease. So the presence of residual virulence was there. The paper was finished by showing that 1 pig that was directly inoculated and 1 pig that was infected by contact, they successfully survived the challenge with the Armenia virus. My point on this is that we have to be a little bit careful with the low virulent field isolates, since the problem of remaining with residual virulence. And I think that should be a point of concern in the use of this virus as a potential vaccines in the field. The second group of way to produce attenuated strain of virus was by passing the virus in tissue cultures. And that's something that there are several examples out there. I just picked one that is a paper from Ruiz Gonzalo back in 1986, where the person worked for a long time in Spain. What he did is pick several field isolates in Spain that were temporally and geographically related, and they passed those isolates in Vero cells. And what he saw is that when bypassing the virus in viral cells, they became attenuated. When he put those attenuated virus in pigs, pigs resist the infection. And not only that, the pigs resist the challenge when the challenge was done with the parental non-adapted virus. He also went a little bit further and trying to see if there were some kind of heterologous protection among these different viruses. And although they were, as I said before, temporary and geographically related, they were not really levels of cross protection. But there was a good example of what the attenuation of virus can be done by passing through culture. I recommend that a paper that had been published by Dennis Kolbasov and his group, that actually is a review that contains all the efforts of his institute of producing producing virus adaptation, and actually we should say attenuation of virus by adaptations in PBMC and other cell lines. And actually, is for those that are interested in this particular theme, I think it's an excellent reading to see how much work these people have done in order to develop what particularly I'm trying to make an example here: the attenuation of virus by passages in cell culture. We have done some of that experience in Plamaila. We try to adapt the Georgia virus to viral cells. And the original idea was, among other things, trying to study what is the correlation of the genetic changes with the process of adaptation of the virus to grow in viral cells, but also trying to see if we were able to produce a vaccine by this methodology. Unfortunately, we failed. Once that we got our virus attenuated, the attenuated virus was not able to produce protection against the challenge. But still, we learned something that I think that was important. That is the huge genomic changes that happen in the virus while the virus is being adapted by passing the virus in viral cells. And this data that is, I would say, an extreme example of gene modification during cell adaptation, we have seen that with other viruses and with other cells. So I would say that the problem of using virus adaptation are the dramatic genomic changes that are involved in this adaptation. And I would say that I will be very careful in handling this virus and attenuating virus in this way, because in our experience, the incorporation of deletions and genetic modifications, it doesn't stop. We have done this with virus, Georgia virus adapted for over 130 passages in viral cells, and we still, in passage 130, we still can see the incorporation of new mutations and new pieces of deletion. So I think it's something that need to be considered if some of the viruses wanted to be used as a vaccine in the field. So the last group is the viruses that are genetically engineered. And I will bring here a cartoon, very old cartoon, I think that was put together by Laszlo Zak and John Nealon at the time that they were working in Plum Island under the direction of Dr. Dan Rock. And basically what these guys did was something that was very important. That is, they developed a methodology to produce genetic modification, gene deletions in field isolate, highly virulent field isolate of African swine fever. Why it was important? Well, because it was the only way to really study the effect of or the contribution of a particular gene to the process of producing the disease in the natural host. By doing so, by first time, it was possible to identify genes that are important in the process of virulence, in the process of producing the disease. 3 genes were at that time identified as such: NL in Spanish isolate, UK also in the same Spanish isolate, I think there was C70, and the 9GL gene in the Malawi isolate. The deletion of 9GL was also done in another isolates like a Pretoria, and they also produce attenuation of the virus. The interesting part of this is that all these attenuated strains, they were able, when inoculated in pigs, to solidly protect against the presence of the disease when the challenges were performed using the parental virus. So these 3 papers were the basis to produce recombinant virus by genetic manipulations, and produce viruses that can be used as a vaccine candidate and protect against the parental virus. And I will not talk about the genome of the virus. Everybody that knows that it's very big, 150 plus genes. The only thing that I would like to mention now is that very few genes out of the 150 plus have been actually really studied experimentally. Most of the functions are ascribed by prediction, but not by real studies in the bench. And I would say that probably one of the best ways to study the function of the gene is by deleting the gene and see how the deletion of the genes alter the phenotype of the virus, in vitro or in vivo. And last year, Linda Dixon presented a paper that I think that was very interesting because a very good review. And basically, she put a table where she identified all the viruses that have been produced by deleting a specific genes or group of genes by different labs. And what I did is I added to the data in this particular table, the data that came in the last year. And basically, we can summarize that 19 different genes have been tested by this methodology. And out of these 19, 8 of those had been genes that were associated in one way or another to the process of virulence in the animal. What I'm trying to say is that these deletions of these genes or group of genes produce attenuation of the corresponding strains, and those strains could be used as a potential vaccine candidate. And I would say that everybody that work with recombinant African swine fever know that this is an extremely, extremely time-consuming, money-consuming, effort-consuming process. But when I see these numbers and say, okay, out of 19 viruses that were produced, almost half of them show that there are viruses, that genes that are related with attenuation and can be used for producing a vaccine. Actually, I think that this very tough work is very, very rewarding. And what I'm going to do is to pass a quick review of the papers that have been published in the last 5 years that are related in the production of recombinant viruses by recombinant virus that can be used as a vaccine candidate. The first virus that was produced in the context of Georgia virus was the one that we did by deleting in NCL. And we published this in 2015. Basically, the virus was attenuated up to 10 to the 3. When we put higher doses than that, the animals die. And that was a very important lesson that we learned, that is not always the same deletion of the same gene, even if the gene is very highly conserved, produce the same effect when done in a different strain. As you see here, the same amount of virus when deleting NGL in Malawi, animals survive perfectly fine. Actually, have been published before that you can put 10 to the 6 of the NGL in Malawi and nothing happens. So we learn a lesson here. The interesting is that the animals that were inoculated with sublethal doses of 9GL were solely protected against the presence of the disease, not of the presence of replication of challenge virus, because some of the animals still produce the virus, the challenge virus replicate, but they were solely protection against the presence of the disease. Lessons learned, 9GL is had to be used in this particular case at sublethal doses. And the other lesson is that, as I said before, not the same deletion and different genetic background produce exactly the same result. And we have seen that later with other examples. The next group of genes that were focused was a group of mutation family 360-505 that map in the left region of the genome of the virus. And we were interested in this region for several reasons. First, this region is deleted in several natural attenuators like the NHP50A or HORT-ADA3. So they could have some relationship with attenuation. Deletion of these areas were associated with the changes in cell tropism, as have been shown, by the group Dan Rock in tick cells. Importantly, several groups have shown that these genes have a good effect in immunomodulating swine immune response, especially the innate. And also important, a paper from John Leland a long time ago showed that he can rescue with this particular area of the genome the virulence of an attenuated virus by recombination. So all of those things put our attention in this particular area, and we produce a virus that we published in 2016, where we delete 6 genes of this particular area, 3 of the 360 family, 3 of the 505 family. And actually the virus, when they put in pigs, even at 10 to the 4, they were completely attenuated. And the challenge with the virus in the way that we do challenge, that's a 10 to the 3 intramuscular animals were completely protected against the presence of the disease, but not always against the presence of viral replication. And this very interesting, Linda Dixon came with a paper a few months after ours, where she published the deletion of a larger area in this particular region of the genome, comprising 9 genes this time, the same 9 genes that are affected in the natural isolate ORD88-3. And she showed that the virus that she produced using Benin as a parental virus was completely attenuated when it was put in pigs, and all the pigs that received this Benin Delta mutation family were also completely protected against the challenge. There were some replication of the virus after the challenge, but there was a solid demonstration that the deletion of this area produce an attenuation and can be used as a potential vaccine production. Interesting, there was a paper just coming in this year from our colleagues in China, Dr. Bu's group, where actually this paper, what this scientists did is to took all the information that was out there about genes that were involved in production of attenuation, and they make all those deletions in using as a template the virus that they isolate in China. So I'm going to refer to this paper several times in the rest of the talk. But basically right now, what I wanted to show is that this group produced also a virus that was extremely similar to the one that we produced in Plum. And this virus that they call 6GD, because there are 6 genes deleted, were completely attenuated, as in the case of our virus at Plum Island. And they were animals inoculated with this virus were solidly protected against the challenge with the parental virulent virus. Interesting, and this is the first time that anybody does this, we recommend virus in African swine fever. They make a reversion to virulent experiment. They pass this virus 5 times successively in group of pigs. And what they saw is that in the 5th passage, 1 pig presents signs of the disease. And when they took the virus from 1 pig, and that pig in the 5th passage, they put in a new group. Now all the pigs showed temperature, and 1 pig showed a very important presence of the disease. I couldn't find in the paper the genomic changes that explain the reversion of virulence. So the genomic changes on the virus isolated in that 5th passage. And I think that will be extremely important to understand how come that the virus that had the least 6 genes now became virulent again. It will be extremely informative in terms of understanding virulence in African swine fever, know which were the genetic changes that support that reversion to virulence. And this is just the summary of the mutants produced by deleting this particular area. Although it's not chronologically ordered, that is what I try to do here, I would like to talk about another virus that was published in this particular paper by Dr. Bu's group, that is the 7GD. 7GD virus is basically the multi-gene family deleted virus plus the deletion of the CD2. In the same paper, they showed that deletion of CD2 does not alter strongly the virulence of the virus. Some of the animals survive, and this lack of effectivity of deleting CD2 as a method for producing attenuation concurs with the data that we produce in Georgia virus by deleting CD2, where we show that by different routes and by different doses, the deletion of CD2 doesn't alter at all the virulence of the Georgia virus. So going back to the 7GD virus, they show, of course, that were completely attenuated when they put in pigs. And interestingly, still, the animals get protected when they were challenged with the virulent virus. More interesting is that the 7GD virus remained attenuated after the 5 passages, where the 6GD failed. in pigs, and also was important, it was innocuous when they were inoculated in pregnant souls. And I believe that this virus is now being used in larger study, including much more bigger numbers of pigs. So I think that it will be very interesting to know what is the status of those results once that they are published. One thing that brought my attention lately is a paper from the PIVRE group where they show something that was not tested before. That is how long the immunity can last in animals that have been inoculated with an attenuated strain. They use two particular viruses, ORF88 and Benin multigene family. And what they show is that animals inoculated with these two viruses, 130 days post immunization, they did not have protection. That was very, very interesting. According with the same result, the paper that I just mentioned, Dr. Booth's paper, they show that 7CD also after 80 days after vaccination, the animals are not 100% protected. They are only 80%, and the titers of antibody are lower. So it seems that there is a problem in the length of the immunity producing by this attenuated virus. This, I think, is a very interesting topic. My only concern is since these three viruses have been produced, the attenuation of these three viruses are produced by deletion of one particular area, that is the multigene family. My question is if that happened with viruses that are attenuated by using deletion of other areas. And that is something that we are trying to prove right now at Plum Island, using some of our viruses that are not related with the deletion of multigene. I wanted to move ahead, and I wanted to talk about the virus that was also published, I think, in 2017 by the group of Dr. Fernando Rodriguez in Barcelona. And basically what Fernando published is a virus that is a BA71 isolate that has deleted the CD2. That is not the only genetic modification that this virus has, if not, because there is some also small changes to make some of the virus inducible. So there are some other alteration of the genome of the virus, but basically the main alteration is the deletion of CD2. They showed that this virus animals inoculated with this virus was completely protected. And interesting, when they were challenged with the homologous virus, they found that the animals were protected against the challenge. More interesting is that they showed that the animals also were protected when they were challenged with a slightly heterologous virus, E75. Remember that the parental virus is Badajoz. And more interesting is that the group of pigs that were inoculated with the BA71 delta CD2 also resist the challenge with Georgia virus. So this paper brought two important points here. One is that the presence of heterologous protection, something that is not very common out there. And the second, that is very important, this virus grows in a stable cell line. I think this virus grows very well in host cells, what it will enormously facilitate the transition of this virus to the industry. I would like to just mention another virus that we produce when we have problem with producing the stability of the 9CL virus in Georgia. We produce a new virus that is the 9CL with the addition and deletion of one gene, UK, that we knew that were attenuated. The region of the UK attenuates some strain of virus. We showed that the deletion of UK in Georgia by itself does not attenuate the virus. But when we put together the deletion of 9CL and UK, we obtain a virus that was completely attenuated even when put in doses of 10 to the 6. All the animals inoculated with 10 to the 4 or higher were protected against the challenge. And interesting, by first time, we showed that protection can be achieved only 14 days after the inoculation of the vaccine in African swine fever. So this virus that we are pretty happy with that because the stability in terms of attenuation and the ability to induce protection, even early protection, and we're still working with them and trying to push ahead as a vaccine candidate. Another interesting piece of information is that in Dr. Booth's paper, they also produce a virus that has a 9CL deletion and a UK deletion. Of course, the virus that they produced was attenuated in animals, but the problem was that this virus, the 9CL UK, the version from Dr. Booth's lab, did not protect against the challenge. And that was something that really surprised us, because we tested several times at Plum Island, our version of 9G in UK, and we couldn't understand very well what could be the differences. And still, we don't understand. We're working a little bit on that. But a brief analysis of the data that published by Dr. Booth show that the deletion of the 9GL gene in the way that they did in Harbin is wider than our deletion. And the reason why our deletion is concentrated in the middle of the genome was to try to avoid the alteration of the genes that are flanking the 9GL, especially B962L gene that is predicted to be an RNA helicase gene. And what we try to do in our deletion is to respect the promoter area of that gene. That's something that is not based in the data published by Dr. Booth. So we believe that probably this deletion alter the transcription of the B962L gene. We don't know if this is exactly the reason why they obtain different levels of protection than us in Plum Island. This is something that we are working in our lab to see if we can show that that is probably the difference. Another thing that was, or another piece of information that was very interesting was published by Linda Dixon by deleting one particular gene, DP148 gene. This gene never had been previously worked in the past, and she used to delete that in the Benin system. And what she showed is the genes map in the right area of the genome of African swine fever. And what she showed is that when the gene is deleted in the Benin strain, they are complete attenuation of the virus. Not only that, if not that, also challenged with Benin virus, in those animals inoculated with the mutant, they were completely protected. Interesting, the protection is achieved even if the animals are inoculated with the virus by intramuscular route or by orally administration, what is very important in terms of thinking administration of vaccine in the field. Dr. Wu also produced a version of this virus, and actually what he found is that the Chinese strain of virus, the deletion of TP148 does not alter yes, the virulence of the virus. So the virus became virulent, and so we are not very sure why, if the difference in the result between Linda group and Dr. Wu's group, but I think that is another nice piece of information showing differential effect of deletions in different backgrounds. And finally, to close this talk, I would like to talk about the last virus that we produce in our lab, that is the deletion of a gene called I177L, again, a gene that had not been previously described. And this gene also mapped in the right area of the genome. And what we did is we reproduced a virus that on the Yorkshire strain. And the first thing that we saw is that the ability of the virus to grow in macrophages is severely affected after the deletion. Still, when we put in pigs, even at high doses, 10 to the 6, the animals were completely healthy. So the virus lost completely the ability to produce virulence. And all these animals were solidly protected against the challenge with the Yorkshire parental virus. We have big expectation in this virus because, again, induced protection even working at very low doses, 10 to the 2, and lacks residual virulence even working at high doses like 10 to the 6. Another thing that I didn't mention is that it does not induce virus shedding. Animals that are cohabitating with animals that are inoculated with even 10 to the 6 for as long as 1 month does not get the virus from the vaccinated animals. And also something that is very important, at least for us, that is induced sterile immunity. And I say this because this is the first candidate that we developed in Plum Island that protects not only against the presence of signs of the disease, presence of the clinical form of the disease, but also when given in the right dose, protect against the replication of the challenge virus. I would like to finish this talk with some gaps analysis, things that I think that should be done. There are several candidates out there, and I think that we should study critical aspect of this candidate, like onset of duration and duration of immunity, genetic stability, attenuation, of that stability. Sorry, how stable that attenuation is. Calculation of minimal protected dose, and also study the possible route of inoculation. Though not all the candidates that are out there, actually, I would say that most of the candidates out there, including us, we don't have answer for all these questions. I think it's very important to standardize the methodology for testing vaccine efficacy. It's amazing when you go through all the papers and the amount of variables that are there is amazing, starting from the type of animal that we use, the dose of the vaccine, the route of the vaccine, and very, very important, the challenge, how we challenge our performance in terms of how much virus it's using the challenge. There are a huge heterogeneity in that, and I think that we should try to standardize a little bit that. I think it's time to start developing vaccine candidates that has DIVA capability. I think it's important also to start investigating the basis why there are differential effect of deletion of one particular gene, even if the gene is very well conserved, when the deletion is made in different isolate. And I think that this is not only academically important, if not that it's important in order to create knowledge to when we had to do this kind of deletion on new strain of virus, we will know which deletion, which genes are more stable in terms of producing the same phenotype. Finally, I think that we should continue discovery and characterization of virus associated with virulence. I think that this is the basis of showing where we are right now. I think that the huge amount of investment that we means all the lab working in virulence in African swine fever had done are the basis of why we are now close to have something that can be considered as a vaccine, and that is probably why commercial partners are start being interested in helping and pushing these vaccine candidates out there and make of those real vaccines to be used in the field. Sorry if I went over a little bit in time. I appreciate the opportunity to give this talk. Thank you.
Thank you, Manuel. We have one question already. It says, live attenuated vaccines seem to protect pigs if homologous. Are these vaccinated and surviving pigs still infectious for other non-vaccinated pigs?
I think that that's well, this is part of the question that we don't know. We don't know. We don't have the answer. I think that one thing that I learned working for almost more than 20 years with this virus is that you better do the experiment and then you answer the questions. I really don't know. The possibility is there, of course.
What are the prospects for live attenuated vaccines to induce heterologous immunity? Is it just the right genes have not been deleted, or will a cocktail be needed? Maybe GARA should play a role in recommending standards across labs.
I think in the last slide, I'm trying to answer that. We don't know what are the basis of cross protection. We don't know what are antigens that are involved in the process of crop protection. So I think at this point, everything had to do by trial and error. Probably in the next talk, when they were going to talk about subunit vaccine, we can put some more light on this. But basically, right now, I think everything had to be answered by trial and error. You got your virus, and you make a test, cross protection test, and see what happens. And this is not only in African swine fever. You go to the fundamental world, it's exactly the same. It's very difficult to predict crop protection from just a sequence. You need to have the actual data.
What is the status of a good cell line for growing Georgia for production?
I don't know. There are papers there that say that there are a nice paper published by Linda Dixon, where they show that by using ZMAX cells, they grow Georgia virus. I do not know any other cell line that have been published right now that support the growth of Georgia virus.
Does the Delta I177L inoculated pigs have joint swelling?
we never observe in the type of experiment that we conduct, we never see any negative clinical aspect of the inoculation of 177L.
Can Delta Chi-177L mutant be produced stably in cell culture?
We are working cell culture. I imagine cell lines, right? The cell culture are primary macrophage, yes, of course. On the cell line, that is an issue that we are working right now in our lab.
Can ASF live attenuated vaccines recombine or regain their virulence?
Well, that is why I think it's so important, the data from our colleagues in China about the 6GD virus that revert after the 5th passage. I think that the data, maybe I was unable to find the data in the paper, but I think that the genetic information regarding what happened in that virus, it will be extremely important to understand reversion to virulence. To my knowledge, this is the first reversion to virulence that have been shown in any recombinant virus. But it's true also that it's the first trial where a reversion to virulence experiment has been really conducted. So,
MA104 cell line is possible for vaccine production?
No. That cell line worked very well for the detection of infectious particles from using different isolates, but does not support efficiently the replication of the virus in large scale.
Questions? So,
okay.
Thank you, Manuel. Very nice talk.
Thank you. Yeah, thank you.